Um, Good morning, followers. Good morning, brothers and sisters in the academy. Today's video is focusing on data transformation. Before we dive into a deep explanation of this concept, I think it is important to import our user data so that we follow the steps as we go along. We import, I always have my data available. Imports first row as variable. You say, okay, the data has been imported. Let me clean the data a bit by keeping the variables that I'm interested in. Real GDP, inflation, revenue, government expenditure, money supply, total debt, political stability, corruption and political stability. I think these are the key variables we are going to get. Now, it's very straightforward that we have clean data. We have clean data to tell you. When you are dealing with data, it's always important to declare time series data as time series. If it's a panel data, then you have to declare it that this particular data that I'm dealing with is a panel data or cross-sectional data. In our case, since we are dealing with time series data, then it is important to declare our data as time series to data, which is very important. Having done that, as I said inter earlier, we are going to deal with what we call data transformation. Underneath, we deal with what we call logging. Logging a variable, differencing a variable. We'll do something related to what we call interpolation. Sorry, is a text. So if I'm typing text, then I have to introduce this asterisk. Then stay again, then we have extrapolation. These are the key concepts that we are going to deal with as far as this video is concerned. A data transformation changes the shape of a data to satisfy statistical property. Example, that is the mean, the variance, I expected to stationary, to be stationary over time. So that's the basic understanding of data transformation, which helps you to address problems of outlier. Helps you to address problems of outlier. In other words, ensures that non-normality variables become normal. An outlier, for instance, if you have a series of variable 9.0.9, 0.8, 10.5, 14.6, 14.6, 14.6, no, yes, 14.6. We have 13.0. Then suddenly we get something like 98.8. The 98.8 introduces what we call an outlier, because if you look at the coefficients here, these are smaller, very small coefficients. But we have a variable, an index that is onto 98.8. If you run your model, if you carry on to model this kind of data, you end up having problems. In sense, you will not get a kind of significant output result that will provide you policy implication. So data transformation helps you to address change. Data transformation becomes handy when you want to test for stationarity, basically for stationarity, to determine the right model to use. For instance, if you are running a stationarity test either using the Kifula or Filiperon, and the outcome of your test becomes I0. In this case, you have to run what we call an OLS model. On the other hand, if you run a stationarity test either using the Kifula or Filiperon or other form of test, then the outcome becomes that the variables are stationary at I1. In this case, you have to run what we call a var model. Although you need to test further whether there is a long run or a short run. That's something that we'll do later. This video helps you to be introduced to what we call data transformation. So when we talk about linearism, talk about differencing in advanced econometric analysis, you'll be able to know. So I1, you have to run a var model. In other cases, when your stationary test comes out that your variable is a combination of I0, combination of I0 and I1, You have to run what we call an ARDL model. ARDL model. So data transformation becomes handy purely in handling this. So we said we are to treat what we call logging a variable. Logging a variable helps. This helps to linearize exponential variable. Assist interpret coefficients in elasticity form. It addresses what we call heteroscedasticity. Address the problems of heteroscedasticity. This is an econometric situation. Econometric condition. Econometric condition where the variance of the stochastic term or error term is not stationary. It's not stationary across the observation. Across the observation. So that's what it is. Now let us linear or log our variables that we have here. Say generate ln of our GDP. Sorry, that was a mistake. We generate ln of our GDP. As ln into our GDP. Further generates ln of INF, which is inflation, equals to ln INF. Generates ln of REV, which stands for revenue, total revenue for the economy. In this case, CLU, ln into REF. You can also type the same syntax in this form. Government expenditure, in this case, consists of both generate ln of government expenditure, which consists of both capital and recurrent, as log into government expenditure. Yes, you can use the same method to log your variable. Ln of what? Public debts, ln of PDA. Public debt consists of both domestic and external debts. The economy of Sierra Leone, in this case, to say ln PD. Yes. generate further ln of M3, which is money supply, the total money in circulation, into M3. Generate ln of 4 indirect investment is equals to log of FDI. Generate further ln of total debt service. Total debt service in this case comprises of both the principal and the interest. The principal and the interest. The principal interest. TDS. Generate further. Yes, let us stop here. Let us don't linearize political stability, corruption, and the product of corruption and political stability and the binary figures, zeros and ones, of our structural break, which is 2014. So let us stop there and see what we've done. Let us browse. And you can see that we have linearized. We have linearized this variable. And if you can observe this keenly, you can see that we have issues of missing values, like the RGDP, the log of RGDP. It has a missing value at the beginning, has a missing value at the end. Others apply the same. So, meaning our observations may have decreased, because the total observation, I'm dealing with the data from 1980 to 2024, which is roughly 45 observations. So having missing value can reduce that observation, so that we'll be able to satisfy econometric property to allow us to run our model. So having done that, let us move into first difference before we start interpolation and extrapolation. Let us do first difference, or differencing of a model. Differencing a model. It helps to reduce what we call trends and seasonality. Trend and seasonality. It helps to correct problem of non-stationarity. Stationarity of a variable to be stationary. To be stationary. In other words, it measures. It's a measure of what? It's a measure. It measures absolute value. It is a measure of absolute value. Measure of absolute value. Etc. That's what difference in a model does for you. And it's very important when you are running stationarity tests for your variable. At times, people move direct from the basic form of the model. They do their first difference or difference directly, which is not appropriate in data analysis. It is good you test the variable at its level without transforming it to see whether it's stationary or not. If it's not stationary at that level, before going to differencing it, try the logarithm. Log your variable and see whether if it's logged, whether it will be stationary at IO. If it's not stationary at that level, then you can go ahead and you difference it. So we do our first difference. In this case, we are just introducing you to be familiar with what we call data transformation. When you talk about log your variable, you know the syntax or the correct method to apply. When we see difference of variable, you know exactly what to do in advanced econometrics that we have to engage in our future videos. So we say generate. Now we are differencing. Generate D RGDP equals to D stroke RGDP. First difference. Generates first difference of INF inflation is equals to DINF. Generates D rev, which stands for revenue, D dot rev. Generates D government expenditure equals to D dot government expenditure. Generates DPD, which is public debt, the first difference of public debt, to what we call D dot PD. The other method of writing your first difference syntax could also be given as what? Generate D1 M3, which is money supply, to D1 dot M3. Right? You can also get your outputs correctly. FDI is equals to D1 dot FDI. Total debt service generates first difference of total debt service, DTDS is equals to D1. Let me use the first one, right? The first approach, D1 TDS. So you can see that on our selected variables, we've also first difference something here. Then in our first differencing as well, we can see that there are some missing values which have the tendency of reducing our observation. Have you ever witnessed or experienced a situation wherein your observations are not complete or incomplete? Then because of low number of observation, you will not be able to run your model until you get the required number of observation. So if you have data, as we all are aware that most of the developing countries' data or indicators are incomplete. So you find a way of massaging, in other words, to manage your data in order to get a complete data so that you can run your model and get a policy recommendation for your account. To do this, we do what we call interpolation and extrapolation. But before going into interpolation and extrapolation, let me give you another idea about difference. Usually, after first difference, it's not statistically, it's not econometrically correct to apply a second difference in a model. So no, this variable is not stationary at its level. It's not stationary when logged. It is not stationary as first level, first difference. Now let me jump to second difference. Don't do that. Don't do. Don't do second difference. Don't apply second difference. Second difference of variable. But if your variable is not stationary at first difference, it is only second difference that is stationary, and it's very important in you. You want to include it. Being that the policy says, the regulation, how do you call it? The property of econometrics, saying that it should not difference, you should not apply a second difference variable. Your option might be to drop it because the variable is not stationary at any satisfactory level, either I0, I. So there is a check. Don't apply this. Let me give you for example. Say D2 second difference of a variable, say RGDP. Don't second difference where you have this RGDP. It can give you answer, but it is not correct. But what if your variable is very important to be used in a model? Do you want to drop it? The alternative way to recheck, to reassess your variable to see whether it's stationary at 0, 1, first difference. You apply what we call AO. AO is what we call innovation outline. You apply that one if it's not stationary at any level. You apply AO, which is additive outline. If you apply these two approaches, you must discover that variable that was not stationary at its first difference at level is stationary at least either I0, I1. Most of the problems that happen here, a variable might not be stationary at either I0 or I1. Possibly it has what we call structural break issues. For this test, the innovational outline and additive outline help you to address it. So you see that instead of dropping a variable, be able to incorporate it. Now let us treat what we call interpolation. Interpolation. There are times you download your variable, you've cleaned them well, and you see that they are missing value within and at the beginning or at the end of your data indicator. You may want those areas to be filled, and you cannot just take any arbitrary figure, value, to feed them in. You have to use econometric approach, scientific approach. So to address missing values within a variable, maybe like from 1980, I'm using 1980 to 2020. In this case, let us say from 1980 to 1990, we have data. But from 1990 to 2000, we have missing data. 1995, we have missing data. Then we have other data from 2000 onwards to 2020, or maybe at the end of 2025, we don't have data. So we need to use what we call interpolation to fill missing data in. So since our variable here, some of our variables have missing data, especially those that return from. Let us use interpolation. Where this variable, the linear ones. So we hypolate which variable? This one here, comma, it generates lin GDP underscore I, which stands for interpolation. We hypolate lin of inflation here, comma, it generates lin of inflation IN underscore I. Here hypolates what we call a lin revenue. Here generates in rev underscore I. You can also hypolate lin of government expenditure. Lin of government expenditure. Lin of government expenditure here, comma, generates lin government expenditure. You hypolate what? Public debt, lin of public debt. Here, comma, generates lin of public debt underscore I. He hypolates lin of money supply M3 here, comma, he generates in M3 underscore I. Further hypolates the subsequent variables. Which one do we have here? After money supply, lin of FDI now is equals to, no, not equals to, here, comma, generates in FDI underscore I. Think we have more? Yes. Total debt. We hypolate lin of total debt here, comma, generate what? Generate lin of total debt service underscore I. So we've done justice to this data by ensuring that we fill some of the values in between. So from the basic form, we've transformed to linear, from linear, fourth difference, from fourth difference, we isolate. But you can see that the isolation still have missing value at the beginning, meaning maybe at the beginning or at the end, these same variables actually have isolation there, missing value. So to address that problem, you apply what we call extrapolation. We apply what we call extrapolation. Extrapolation in a variable. So we use the same variables. Now the ones that we interpolated, that has helped us to fill the missing value in within the indicators. To address the problem of missing value at the beginning, either at the beginning or at the end. So here, this is the syntax for it. You hyperlink. What variable are you going to have? This one. Here, then it generates this same variable underscore e. Yes, equals. We isolate again a line of inf underscore I here comma, it generates line of inf underscore I underscore e equals. It further isolates revenue here generates line of rev underscore I underscore e equals. Further extrapolate what? Government expenditure. Government expenditure, comma, generates line of government expenditure underscore I underscore e, then you see equals. It isolates line of public debt underscore I here generates line of public debt underscore I underscore equals. It isolates which variable? Money supply. It isolates money supply, line of money supply. Make sure that you write the variable the way they are written. Otherwise, you will not get a correct syntax. This is very important. Generates into line M3 underscore I underscore E equals. Where we are, we have money supply. Money supply is here. What variable next? FDI. We isolate line of FDI underscore I here, I generate into ln of fdi underscore I underscore E, then equal it. Also give an extrapolation of what variable after fdi. After fdi, we have total debt. Ln of total debt underscore I underscore I underscore I here, comma. Then we generate ln of total debt service underscore I underscore E, then we equal it. I think we've transformed this also from its basic form. We've logged the variable, first different variable, but to focus on the linearized variables. We observe some kind of missing values both within and at the beginning and at the end of the variable. So what we did, we applied both interpolation and extrapolation. The extrapolation is the last one. So you can see now that the first set of the variables here, the isolated ones here, they have missing values. Like the RGDP has a missing value. There are others that also have missing value. Then we try to fill that. Then we still have a balance of other missing values, either at the beginning. But now, if you look at this point from real GDP, when we apply interpolation and extrapolation, I stand for interpolation, E stand for extrapolation, which we will apply. If you go through these variables, you can see that all the variables are filled. We have complete data. So you can use this to run the model. Now, let us see. Let us run a simple model, wireless model, and see what will come out. Three different. Let us run this basic form of variables. Sorry for the time, but this is important when you start running of when you start a video, the particular concept, make sure that you do that. This is the first model, wireless model. When the variables are at level, they are not transformed. Now let us see when they are transformed when we use linear. RGDP, inflation, of inflation, government expenditure, right? Total debts. Now, this should not be. Stops at 7. Remove this one. Now you start seeing some satisfactory of statistical significance. Let's look at when with first difference. When the variables were first difference, and see what will be the outcome. Always when you are specifying your model, make sure that the dependent variable first, followed by the independent variable. That's what I'm doing here. As a researcher, you must know your dependent variable and your independent variable. Always ensure that when specifying your model, your independent variable is first. a dependent variable comes before the independent variable. Go on. This is the first difference, output, without taking into cognizance which variable that is stationary and which one that is not stationary. This is just a simple for us just to see what will be the output. Now, if you go to the advanced level, when you want to run a clean model, you must ensure that you don't just force difference of it. Difference it when it is not stationary. I'm just giving an example. So let us see when the variables applied interpolation. 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 What's happened is we interpolated also. The variables are, you see, a kind of just one that is stationary that shows a kind of a significant output. Inflation is negative and stationary at 1%. Statistically significant at 1%. Now, let us see what this can help us when we go to the hyperpolation. The extrapolation big debts, then FDI, total debt service. So this is the output for different variables, and we can see that these variables, because of the arbitrary logging, differencing, interpolating, and extrapolating, we don't have much of statistically significant variables. Besides a linearized model, where we only have how many variables? We have inflation, it's significant at 1%. Yes, of course, public debt is significant at 1%, shows a positive impact, meaning this economy is using public debt for the objective purpose. This is significant, slightly above 5%. It means significant at 10%. At least this can give you some stories if you want. But if you look at the non-transformed data, of course, there is no variable here that is stationary, significant. None of the indicators or the coefficients is significant. So this approach is actually introducing you when you want to do your formal model, what you need to know as a basic. When you want to test for stationarity, what are the methods? That's just basically just applying here. For advanced level now, these things come handy when you are doing the advanced econometric analysis. Right. So for colleagues that are interested, if you want clarity, you want data, you can send email to econometric.research@gmail. So if you want data, you want clarity, or maybe you want the do file. If you want the do file, you can also send message and email here. I will respond to you so that we build this platform. I think so far this is what we we have today, or what I have for you today. One, we've gone through what we call data transformation. Data transformation. Underneath we have logging a variable. Subcomponent we have logging a variable. We have what we call difference in a variable. We've also gone through what we call interpolation. Interpolation. Then we also do what we call extrapolation. Extrapolation. Then aside, we talk something related to what is the importance of using innovative IO. Innovative. Then concept related to what we call AO, which is additive outline. So thank you, friends. Follow, share, and invite colleagues to be in this platform. Thank you.